All right, so guys, we're going to start in on chapter 13.3. We're finally to the big part of chapter 13, which is the probability. This is what 13.1 and 13.2 is gearing you up for. And today we're going to construct probability models. We're going to look and compute probabilities of equally likely outcomes. And then last but not least, we're going to use the addition and complement rule. I'll talk more about the complement rule on Monday. So let's dive in. First things first, an event is an outcome from an experiment. So one you're most familiar with, at the Super Bowl, what do they do at the Super Bowl to get this thing started? Nope, even before that, they flip a coin, right? And on one side is heads, and the other side is tails. So when we flip a coin, that's our experiment, and the event is either heads or tails. Okay, now the probability of an event is a measure of the likelihood of the occurrence. Okay, and a probability model lists those outcomes of the experiment. So when we take a look, the probability of getting a heads, so P for probability of heads, is going to be a what? What percentage? What do you guys get? 50%, which is one heads out of two possibilities. Okay, versus probability of tails, T for tails, is 1 out of 2. When you look at these probability models, they will always add up to 1 or 100% if you're looking at percentages. Okay, so if you're looking at the fractions, or they could have made this like 0.5 and 0.5. So fractions or decimals will add up to 1 if it's a probability model. Or if you're looking at percentages, you should get 100%. So that's one of the questions that we ask you guys. We'll give you a list of a probability model, and we'll ask you guys, is this a probability model, yes or no? And it's all based on adding up the numbers to make sure it adds up to 100. If it doesn't, then the answer is no. Whether it's above or below 100, then the answer is no. Okay? So the next thing is we're going to construct probability models. We need to know the sample space of the experiment. Okay? So sample space is the key word there. This is the set S can list all the possible outcomes of the experiment. So for example, my set would be heads or tails. And my size of this, we count how many we got, and there's two possibilities, either heads or tails. Add them together. Okay? So we're going to go through and answer some of these questions like you're going to see on my math lab. It says determine the sample space resulting from the experiment of rolling a die. Now, I would assume that we all know how many sides there are in a die and how many numbers, right? All right, so sample space. We know how many numbers? 6. Whew, good. There are 6. 1, 2, 3, 4, 5, and 6. So there's my little fancy brackets. Okay, so again, those are all my possibilities. And then the sample size is 6. Okay, now, example 1B, I'll call it, is what do you do when you have 2 dice or 2 die? Okay, what is the sample size then? So when we take a look, this is pretty much what we learned in chapter 13.2. On the first die, we have 6 choices, right? And on the second die, we have 6 choices. Well, what do I do with those? We multiply them together, right? This is my appetizers. This is my entrees. This is the how many choices I have for the first die, 1 through 6. This is how many choices I have for the second one, 1 through 6. And I multiply them together, and I get 36. Okay, so 36 possibilities. multiply. Multiplication principle of counting. Now I could list those all out if you really wanted me to, but I think we know what would happen, right? We would roll a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6. And then go across and do the 2s. I could do a 2 and a 1, a 2 and a 2, a 2 and a 3, 2 and a 4. And I do that 36 times, right? The idea is you would have a 6 by 6 grid, right? And you'd just be filling in the numbers 1 through 6 and 1 through 6. Okay. That's easy peasy, right? All right, so let's move on to the next pot. It says here probability for equally likely outcomes. Pretty easy stuff. It says in an experiment, n equally likely outcomes. If the number n is the equally likely outcomes, and if the number of ways an event E can occur is m, then the probability is E. Okay, of E is this. I have m over n. So if we look at heads, right, the probability of me rolling a heads or flipping and getting a heads would be 1 out of 2. There's one head out of 2 possibilities. Okay, that's the idea of that box. Okay, the probability of me of rolling a 1 on a normal die would be a 1 out of 6 possibilities. Okay, so example 2 says a classroom contains 20 students. I have 7 freshmen, 5 sophomores, 6 juniors, and 2 seniors. A student is selected at random. So Mr. Gotsch is walking around with a blindfold, and I just grab one of those kids. And I look and I see who it is. It says construct a probability model for the experiment. So again, my set, I would have 7 freshmen, or frosh for short. I would have what? 5 sophomores? 5 sophs. I would have 6 juniors. And then I would have 2 seniors. And my sample size, we know, is 20 students. Okay? Now when I create the probability model, I'm going to figure out the probability of grabbing each one of those. So what's the probability that I grab a freshman? Probability, P for probability of a frosh. How many freshmen do we have? We have 7 freshmen out of 20. Okay? Now, if my math lab wants a fraction, you can give the fraction. If they want a decimal, so take 7 divided by 20 and figure out what decimal that is. Or if they want a percentage, take 7 divided by 20, get that decimal, multiply by 100, and we should get, what's 7 over 20? Shout it out. Calculators, mount up. What is that, 35%? Is that right?
Yeah.
7 over 20? 35%? That's okay. So we go through and we do that for everybody. So I take a look. I look at my sophomores. So probability of a soph. I take a look. There's 5 sophomores out of 20. Now again, if they want fractions, don't give 5 out of 20. They always want you to simplify. So R that thing, reduce it. And that's what, 1/4, which we all know is 25%. Okay. So if you're given a fraction, there we go. And then we go through and do the last two for like a probability of getting a junior at random. There are 6 juniors out of 20. Well, that's 3 out of 10, which we know is 30%. And then last but not least, probability of getting a senior. Okay, so if I want a senior, I take a look, there's only 2 of them. That's 2 out of 20, reduce. We know that's 1/10, which is 10%. Okay. So as I take a look, guys, this again is what a probability model entails. Okay. It has your sample space, it has your sample size, and then it has the probabilities of all of those things happening. Okay? Now, percentage-wise, they should always add up to, again, 100%. So they might give you something like this, and they'll say, is this a probability model? And again, if it does not add up to 100, then it's no. How's that? Any questions, y'all? All right, all right. Any questions at home? Let's get some thumbs here. Where are we at with thumbs? 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 Do I have any thumbs? Thumbs up, Mr. Gotsch, this is easy. Oh man. Now I'm worried though, because that's what you said on the test, for the test, the quiz on that stuff. And we had a lot of good grades, but we had a few that were not so good. Oh man, I hope you guys will review that last quiz. If you put in a mistake or something, let me know. All right, so now the next one is the addition rule of probability. This is known as the mutually exclusive event, what to do. So it says E and F are mutually exclusive events, meaning they have nothing in common. Okay, one event doesn't apply to the other event, so they're separated. So if I want the probability of E or F happening, E union F, then take the probability of E and add it to the probability of F. Okay? Again, mutually exclusive means there is no intersection here. They are separated. They're disjoint. Just like these spinors, there is no overlap of these spinors. We have two spinors here. So the experiment consists of these two spinors, spinor 1, spinor 2. Asks you to construct a probability model. And what is the probability of getting a 2 or a 4 red? Okay, so the first thing is I always like coming up with my sample size. So my sample size. How many choices do you have on the first spinner? You guys got 4 choices there. How many choices do you have on the second one?
2.
You got 2. This is my appetizers. This is my entrees. This is the choices for the first one. This is the choices for the second one. I multiply. There are 8 different combinations or possibilities. That's going to be my divisor. Okay, now you could list all 8 if you want. Okay, so I'm going to go ahead and do that over here. So this is my probability model. The probability of spinning a 1 and a red, I'll do 1 and R for red. Or I could spin and get a 1 and a blue. Or I could spin and get a 2 and a red. Or I could spin P for probability and I could get a 2 and a B. Blue. Halfway, 3 and a red, 3 and a blue. Or I could get a 4 and a red and probability of a 4 and a blue. Now, each one of these all have the same probability, which is 1 out of 8 happening. So the probability of me getting a 1 red would be a 1 out of 8. Probability of 1 blue would be 1 out of 8, and so on and so forth. Well, the question that they have now is, once I've set this all up, what's the probability of getting a 2 or 4 red? Okay, so the question is, what's the probability of 2 or 4 red? Well, that means I got to take the probability of a 2 red and the probability of a 4 red. And what I need to do is add them together. The probability of a 2 red would be 1 out of 8, and the probability of a 4 red would be also 1 out of 8. Again, we just add those 2 fractions together. So 1/8 plus 1/8, we know is 2/8. which we know reduces down to 1/4 or 25%. Okay. So the idea is, if I look at my probability model, I wanted to know what's the probability of me getting a 2 red or a 4 red. Well, that's 2 out of 8 possibilities. Okay, just add the 2 fractions together. That's the idea. Okay. All right, do you guys have any questions with mutually exclusive events and what to do with those? So I'll go through some more examples here. Okay. And for us to understand example 4, you guys have to have a little bit of a background of cards, because it says, what's the probability of selecting an ace or king of a standard deck of cards? Well, when we look at a standard deck of cards, you have to know a little bit about these things. Now, if you don't know much about cards, you'll be fine, because number one, you can always Google. I literally Googled deck of cards, and this is the first image that came up. Okay. First thing is, you got to know how many cards are in a deck. There are 52 cards. If you don't know, now you know. There are 52 cards in a deck. So if anybody says, hey, do you want to play 52 card pickup? The answer is no. Because they'll say, if you say yes, they'll take a deck of cards and throw them on the ground. And then you have to pick up 52 cards, right? 52 card pickup. You're picking, oh man, did anybody get suckered on that when they were a kid? Yes, I did. My brother did it, the dirty dog. So there's 52 cards. Now, they are split half and half. Half are red, half are black. All right, so that means there's 26 red and 26 black cards. Okay, those have been split into suits. So there's 2 black suits and 2 red suits. Okay, suits mean what type of card. This is a club, this is a spade, that's a heart, and that's a diamond. So hearts and diamonds are the red ones, spades and clubs are the black ones. Now, some of you guys are like, I know this movie guns. Well, there's people that have never known that. So I'm just teaching those people, right? So now, if I take 52 and I divide it into 4 groups or 4 suits, thank you. There are 13 in each suit. Okay, so there's an ace, which in blackjack could be a 1 or an 11, but we'll count it as 1. So 1 through 10, so there's 10 cards there, and then jack, queen, king is the 11th, 12th, and 13th card. So there are 13 cards in each suit. So these are things that you guys should know when we're talking about cards. Again, at any point you ever need, we're doing all this stuff on our computers, you can always pull this stuff up, or if you're in class taking a quiz or test and you want to see this, I'd be happy to project this up for you. Okay? All right, but most of you guys know this stuff. Anyways, what's the probability of selecting an ace or king? Well, we got to know what the ace is. A is the one with the ace. Aces are A's. How many aces do you see? 4. And how many kings do you see? 4. So if I want the probability of an ace or king, AK for short, all I got to do is take the probability of an ace, take the probability of a king, and add them together. Okay, these are what we call mutually exclusive. So there is 4 out of 52 aces, and there's 4 out of 52 kings. And if I add those together, I get 8 out of 52. And math frac that if you want. If you want a fraction, r reduced by 4. And we get 2/13. Or throw it in your calc, 2 divided by 13 or 8 divided by 52. How much? 15.4? Mm-hmm. Perfect. So it's about a 15.4%. So sometimes people like watching like ESPN2 or ESPN3 or whatever, and they have Texas Hold'em. You guys ever watch Texas Hold'em? So sometimes they'll say, oh, this guy needs this on the flop or this on the river or whatever. And you'll see a percentage, right? Well, that's what those guys are doing. They know how many cards are left. They know what he needs. It might be, he might need a heart, they know how many hearts are left in the deck, so they're taking that, and that's their probability. Okay, he might need an ace or a king to beat. Who knows? Depends on what kind of full house he's looking to get or what have you. But that's the idea. That's what they're doing. That's what that little percentage is. Okay, do you guys have any questions with that? All right, we will talk about what not mutually exclusive is, and I think cards is the best example of that. Well, let's move on to number 5 and 6. When I take a look at example 5, it says determine the probability of having 3 girls in a 3-child family. So determine the probability of having 3 girls in a 3-child family. So the first thing I'd want to know is sample size, right? So when I take a look, 3-child family, I have a choice for the first child, choice for the second, choice for the third. And it's either boy or girl, right? Boy, girl, boy, girl, boy, girl. There's 2 choices for the first, 2 choices for the second, 2 choices for the third. What do I do with all those numbers? Multiply. Very good. This is my appetizers, my entrees, my dessert. This is the choices for my first child, the second child, third child. Multiply. There are 8 possibilities here. Okay. Now, some people want to be able to visualize that, and it's totally fine. I'm going to do that over here just so you can see it, but you do not have to do it, like on a quiz or test or anything, but some people like to see it. You could have a boy, boy, boy. You could have a boy, boy, and then a girl. You could have a boy, then a girl, then a boy. You could have a boy, a girl, and a girl. Oh, man, you could have a girl, then boys, BBB, or GBB. You could have a girl, then a boy, and then a girl. You could have a girl, and then a boy. Or you could have a girl, girl, girl. And that's all 8 possibilities, right? Well, what's the probability? Determine the probability of having 3 girls. What's the probability of getting GGG? Well, all of these have a probability of 1 out of 8. So the probability of having GGG would be 1 out of 8 probabilities there. Okay? So the next part, example 5A or B, whatever you want to call it, says what's the probability of having 1 girl? Just 1. The rest boys. So then you have to look in all the different ways that you can get 1 G, 1 girl. Okay? So probability of BBG, probability of BGB, or the probability of GBB. All right? Each one of these is 1/8. 1/8. 1/8. And what do we do with these fractions? We add them. Each of these are mutually exclusive. Add them together. And we get 3 out of 8. 3/8 is, what is that, 37.5%? Okay? And again, the idea is when you have the whole probability model, you could also just look and highlight the ones that just have the 1 G here. And there's your 3 out of 8 possibilities. Okay? All right. So, could you imagine having 3 girls in your house? Holy cow. I lucked out. I got BBB. I have all boys in my house. That was a 1 out of 8 possibility. Yeah? Oh, man. My household, a little different than my brother's. My brother is the opposite. He's got 3 girls. He's got GGG.
What are the odds for that?
1 out of 8. Look at that.
Yeah.
Right? What's the odds of that? Then I'm 1 out of 8.
Like a difference between like girls having a higher chance of being born than guys.
Well, the woman has, from what I understand, 2 X chromosomes, and then guys have an X and a Y.
Yeah, the guys.
So the guys decided they either give the X chromosome or the Y chromosome. Now, you would have to ask Mr. Rogers or Mr. Brunswick in biology, but I'm pretty sure that's how it works. Okay? All right. There's your biology lesson for today. Oh, man. Here we go. Last but not least, I got two more examples, guys. Example 6 says, in the experiment, 2 fair dice are rolled. Determine the probability that the sum of the dice is 5. We go back to how many possibilities are there? Do we remember? 36. How'd you do that? Yeah, 6 choices for the first, 6 choices for the second die. That's 36 possibilities. That's my sample size. Now, for me, I don't want to write 36 of the possibilities, right? That would take a long time. So what I would recommend is just writing the ones you're looking for. And we're looking for a sum of 5. Okay, so probability of getting 5. Well, that would be like 3 and 2, right? What else?
4 and 1.
4 and 1. More. Give me more. 2 and 3. 2 and 3 and 3 and 2 are different. So you want to include it. And then probability of 1 and 4. Each of these have 1 out of 36 possibilities. And then final answer we get is 4 out of 36. Reduce that, reduces by 4, that's 1/9, which I believe is 11.11%, something like that. Okay. Question on what's the probability of getting 4? Just 4, a sum of 4. What's the probability of getting a sum of 4?
Would be the same.
And everybody thinks, well, wouldn't that be the same? And the issue when you're dealing with the doubles, like roll a 1 and a 1, those only happen one time. So when you guys roll doubles, those are only, if you go and do the 6x6 grid, the 36 boxes, the doubles only happen one time each. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6 only happens one time each. Okay, that's why Yahtzee is worth so many points. It's because it's very hard to get the doubles and the 1s and the 2s and the, okay? So be very careful when if you're including 1, 1 or 2, 2, that only happens one time. Okay, and if you don't believe me, write out the 6x6 grid. And I promise you it's only going to happen on the diagonal going down across. Okay? All right, last but not least, addition rule of non-mutually exclusive. Okay? If I want the probability of E or F, we take those two and add them together. But if there's some overlap happening, we have to subtract the overlap. And the best thing I can do is come up with this example for you guys, and I'll show you the picture. They want to know what's the probability, okay, so what's the probability of an ace or a club? Okay, so let's see what that means. Okay, so let's take back out our picture here. All right, so we're almost done. All right, so do you see my aces? We have 4 aces, right? But then I have all these clubs. So if I add up all my aces and all my clubs, do you see the problem? I add up all my aces and all my clubs. I just counted this guy twice, right? That's the overlap. So I either have to exclude it on one of them or subtract it at the end, okay? So that's what this formula is saying. Take the probability of an ace plus the probability of clubs, but then subtract the ace of clubs. So again, there's 4 aces out of 52. there's 13 clubs, 13 in each suit out of 52, but I just added that ace of clubs twice, so I've got to subtract it. Okay? So we end up with 4 plus 13 minus 1 is 16 out of 52. And 16 out of 52, I think, ends up to be what, 4 out of 13? Which is what percentage? 30.8. Okay, so I hope that helps with understanding what would non-mutually exclusive. It's where the overlap would happen. So that's why it's nice if you do have this sheet. You know, if I'm looking for my ace of clubs, if I'm looking for the probability of aces and clubs, well, I could just go 1, 2, 3, 4, and then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and now I don't have to worry about adding this one twice. Okay, so that's the idea. Ladies and gentlemen, that is all I have. Do you guys have any questions?